All right, talking transformations today. So we're transforming our functions, which is similar to transforming like you did back in geometry, but we're only doing it to functions. We're not doing it to shapes or points or lines or anything along those lines, that aspect. So transformations of functions have a specific order that they go through, and this is actually that exact order. So any horizontal shifts happen first, and then dilations, reflections, and your vertical shifts come at the end. And it's all because of the way that the equations are written for your functions. What you're doing is you are working with what's closest to x, which would be your horizontal shifts, and then your dilations, reflections, and vertical shifts. So I'll show you what I mean by that after we go through what's happening here for each of these. So our horizontal shifts are the ones that move left and right. Those horizontal shifts is what moves our graphs to the left or to the right. So our notation for that is the value is inside the parentheses with x. Generally, it's represented by the letter h. H just is some number. So if inside those parentheses you have a positive h, that's going to make you move to the left. That's a plus sign there. Because you're supposed to subtract h. So remember, minusing a negative is what turns it positive. So you'd be minusing, say, -5. So you're going to the left. That's why positive ends up going to the left. H is negative. That means you plugged in a positive number for h. So you're going to be moving your graph to the right. So take a look at an example over here. So let's say we have f of x equals x cubed. We'll do our parent function for our cubic graphs right there. So now let's move that to the left. So notation-wise, that's going to look like this. This is our function notation telling us to move 3 to the left. This is what it would actually look like in the function. And then on the graph, it has the same exact shape. It's just 3 units to the left. Or if we decided to go to the right, again, here's our function notation of how that would look. Here's what it would look like in our actual equation. They would put parentheses around it. And that's going to move our graph over to the right there. Those are our horizontal shifts. Next are our dilations. So that's where we either stretch or shrink our function. Words that you used in Algebra 1 would be narrower or wider. Some people would call it flatter for the shrink one. So our dilations means you are going to be multiplying something times your function. Okay. So if your a is greater than 1, that means you are stretching your function. If your a is between 0 and 1, meaning it's a fraction, that means you're going to be shrinking your function, making it flatter. A is always a positive value. If you see a negative sign there, that's actually connected to your reflection. Your a is just the number itself. So let's go over here for our example. So g of x equals the absolute value of x. So we use absolute value of x as our example here. So there's my absolute value of x. Use purple. So function notation, 2 equals g of x. That would be 2 times your absolute value of x. Sometimes they can put that 2 inside as well, and it still does the same thing. It still stretches your function up. And so on your graph, it would end up looking narrower, like my purple one does there. And let's see, are these pink? Oh, or orange. So if we do 1/4 x, or g of 1/4 x, again, it has the same outcome. It makes your graph wider, so like my orange one there. So if your number is greater than 1, it stretches it. So it's stretching from my green line, it's stretching each of those points up, and it makes the graph end up being narrower. If it's between 0 and 1, it makes it wider. All right. So then our reflections, we really only have 2 reflections that we deal with. So a reflection, a generic definition would be flipping over a line. So if the negative sign is out in front of the entire function, you reflect over the x-axis. Because if you remember f of x and y, they're twinsies, so they're interchangeable. So if I make y's negative, I'm going from being up in the positive. So I'm being up here in the positive, I'm flipping it and making it negative. So that one's flipping over the x. Whereas if the negative sign is in with x, you're going to reflect over your y-axis. So if the negative's in with x, you're going to flip over the y-axis. So my example over here, I'm going to use square root function. So there's my square root parent function. So then again, if I put the negative out in front of the entire function, here's what it would look like function notation-wise. Here's what it looks like in the actual equation. And that's going to make my graph flip over my y-axis there. If the negative sign goes in the parentheses with the x, so for this case, it would actually go under that square root sign. That's going to make it reflect over the y. So as you can see, like the negative usually is out in front. So if it's with a 2, like if you have a negative 2, that means you have 2 things happening there. You have a dilation by a factor of 2, and you have a reflection because of the negative sign. Your a is never a negative value. The negative means it's reflecting. And we'll look at some examples in a minute for that. And then our last one here, vertical shifts. So that means our graph moves up or down. So our notation for that is that there is just a number added at the end of your function. Okay. And this one is exactly how you think. If k is positive, you're going to move up. If k is negative, you're going to move down. And again, k just represents a number. Doesn't matter what number. So j of x equals x squared. It's our parent function for our quadratic family. Okay. So if we say j of x plus 3, so here's our plus k, that's our function notation. In our actual equation, this is what it would look like, x squared plus 3. So the entire function, every point on that function is going to move up 3. Just like that. And then if we subtract a number, that means our entire function, every point on that function is going to move down that number. All right. So let's take a look at a few examples. So let's look at that other paper I gave you. Oh, let's zoom out a little bit. So So here's kind of a generic function formula for you. It changes depending on if you have a quadratic or a cubic or anything along those lines, but this is the basic way it looks. So again, your functions follow, the transformations follow this pattern. So here's x, so we're going to start with this horizontal shift, and then you multiply by your dilation, and then if there's a negative sign here for your reflection, that happens next, and then your vertical shift. So we're starting with what's closest to your x, and then we work our way out to everything else. So here, f of x equals the absolute value of x, g of x equals all that. Describe the transformations in order. So first thing is going to be that +3 in that absolute value bars with my x. So that's going to be a shift of left 3. And then I have this -2 right here, but again, that -2 means two things are happening. First, it's a dilation by a factor of 2. And then third one, this one would reflect over the x-axis. Sorry, misspoke. And the fourth thing happening here is that -4, so that's going to make it shift down 4. So if you were trying to graph this without your calculator, let's say for example, you would take each point from your original parent function, you would shift them left 3, and then you would dilate it by 2, and then you would reflect it, and then you would also move it down 4. So each point follows those transformations. Next one. Parent function, square root of x. So then we have square root of 2 minus x plus 5. I like to rewrite that square root sign right there. Otherwise, sometimes you don't always see what the transformations are that are happening there. So that's really the square root of -x plus 2. So this is going to first move left 2. Then it's going to reflect over the y-axis. And then it's going to go up 5. So you got your +2, and then you got that minus right there, which is right next to the x. It's now out in front of the entire function. And then +5. All right, number 3, parent function. Parent function has been transformed. They want us to find h of 1. So we actually don't need to know what the transformations are here. We don't really need to know that it's going left 3 and then up 1, because that's not going to help us any. H of 1 means I'm going to plug a 1 in for all of my x's, even right here in that function notation, which would give me an f of 4 plus 1, because 3 plus 1 gives us 4. So now what I'm going to do is this is connected to this one. So now I'm going to go over here and find f of 4, because it wants f of 4, which is going to give me a 64. So now I have back over to my problem. I'm going to do 64 plus 1. So our final answer is 65. So when evaluating, if it connects back to a different function, you have to hop back to that other function and find out that number. All right. Quadratic function g of x has a y-intercept of 12. What is the y-intercept of the function h of x equals 3 times g of x minus 5? So here we have a dilation by 3. And then our function is going down 5. So as I was saying before, your transformations, whatever happens to the entire function happens to every point on that function. So including your y-intercept. So I'm going to do a dilation of 3 on my y-intercept. So that gives me 36. And then I'm going to move it down 5. Our new y-intercept is going to be at 31. So every point follows the same transformations. Okay. Question 5. This graph over here is the graph of the function f of x, taken care of, we first have to graph g of x, which is f of x plus 3 minus 1. So that's going to be left 3, down 1. Those are our two transformations that are happening there. So I'm going to take each point, I'm going to go to the left 3 and then down 1. Left 3 and then down 1. Down 1. 1, 2, 3, down 1. 1, 2, 3. 1, 1, 2, 3, down. There we go. So there's my graph of g of x, which is my green function on here. Part B, what is the smallest solutions to g of x equals f of x? This is our function notation for intersection. We're trying to figure out where those two graphs intersect. As two intersections here. But they want the smallest of the two. So the smallest of the two is going to be over here. This one's more to the left, which is nice because that actually hits at a nice spot. The first one is like a decimal. Not so nice. And then h of x is my g of x function, but down 3. Explain why the equation h of x and f of x has no solutions. So I'm going to actually move each point down 3. 1, 2, 3. 1, 2, 3. So there's h of x. So the reason why there's no solutions between h of x and the original f of x is because they do not intersect. And then looking at our last one here, we have this equation, f of x equals 2x cubed minus 3x plus 8. So to flip it over the x-axis, I need to put that negative sign out in front of the function. But I need to put it in front of the entire function, so all 3 terms there. And then we distribute it. So then to flip it over the y-axis, I put the negative sign in by x. So negative x cubed is going to be negative x cubed, because negative times negative is positive, but times one more negative is negative again. And that's going to make that a plus 3x, and then plus